What comes into your mind when seeing this? If you are thinking about that food, that sushi, you are not alone. I'm thinking about that sushi, especially that sushi photo file. Where will that sushi photo file will eventually go? Well, it can probably be posted as a post in Facebook or Instagram, or maybe as a tweet, or compiled as a video for TikTok, YouTube, or maybe simply end up stored in a Dropbox. You name it, right? The point is that that photo file will end up somewhere in the cloud, a place we are taking for granted today, but relied on so much on our everyday life. Now, how if I tell you, as we exchanging more and more photos in the cloud, we are actually wasting more and more energy inside the data centers, the actual place where the data exchange is happening. And by 2030, the total energy consumption due to these data centers will reach up to 1,200 of terawatts-hour, with 50% of it will be wasted. This is a really big number, and already twice of Canada national electricity consumption will be used solely for the data exchange. To understand why data exchange takes so much energy, let's see how our data travels between our gadgets and the cloud, where we're exchanging photos, say, among our friends. When talking about data exchange via internet, basically we are talking about a two-way communication between our gadgets and the clouds or data centers. Back in the day, copper wire cable was used to distribute the internet, much like telephone cable connecting our homes and the data centers. And these data centers are nothing else but bunches of powerful computers called servers that interact to each other to perform computation requested by us. And the fact that it uses copper wire to connect to each other makes a lot of power actually dissipate as a heat. As demand for the internet increases, more and more computers are required inside the data centers. This makes data centers become hotter and hotter. Remember, how hot is your laptop, say, after you play your favorite game? And try to imagine how hot is these data centers where we have millions of computers connected to each other at the same time. Luckily, as time goes, those copper wires distributing the internet got replaced by optical fiber. This lowers the energy consumption, reducing the cost, and makes faster internet possible. One thing that is very concerning, though, those copper wires inside the data centers, they are still there. We will come back to this, but it needs sophisticated air conditioner or AC system to be installed inside the data center building. This makes data centers consume much more energy because 40% of this power will be used for this AC system. This is how the actual data centers look like, with one of those dark squares correspond to one computing unit. You see, only with the cabling, it has been so messy. And remember, this forest of copper wire require 40% of the total data center's power consumption. So now, to understand why the data centers still keeping these copper wires, the ancient technology, instead of changing to optical fiber, let's think about how does it take to connect two computers via optical network. Our data inside the computers are essentially electrical signals forming arrays of zeros and ones. And to transmit this electrical signal via optical fiber, we need sort of a translator used to convert electrical into optical signals or vice versa. This equipment is called transceiver, which need to be plugged inside each computer. Inside a transceiver, what we have is basically a laser to transmit optical data and optical sensor to receive this optical data. When transferring a file, for example, what we are doing is basically input our electrical signal into the laser that makes, for example, 101010, that becomes on-off, on-off, on-off for the laser. And this blinking of light then transferred via optical fiber and received by the optical sensor on the other part of the network. And you see, this means that each computer needs to have laser and sensor. The problem with this is very clear. One computer needs to have one transceiver. Remember, we need millions of computers, that means millions of transceivers to be installed. This becoming impractical concerning the cost of installing and operating those millions of transceivers. And essentially, if you remember, in our data centers, we just don't have any more space. This is the big problem I'm going to solve. I want to make those transceivers so small, these lasers and optical sensor, I want it to be so tiny and make it place inside our computer chips, which are based on silicon materials. This will do the following things: solving the energy problem, solving the space problem, reducing the cost because the cost of the materials will get reduced, and also it will make the faster internet possible because everything now will be in the speed of light. For a material scientist like me, this idea of devices integration turns into this materials integration problem. In our case, how to grow indium phosphide crystal, which is a basis of laser, and germanium crystal, which is a basis of optical sensor, on a silicon substrate. For tonight, I'm going to focus on the optical sensor part and save the discussion of the laser part for another day. So here I listed 3 main optical sensor materials: silicon, germanium, and indium arsenide, and how it suits with applications in optical communications, which is based on infrared radiation. First, silicon. Silicon is surely inexpensive with high degree of integrability, but it suffers with very low performance when trying to detect infrared radiation. Germanium and indium arsenide, on the other hand, they have been used for decades to realize detection in infrared radiation. But they are expensive and hard to integrate to silicon. For those of you who are material scientists, when I was talking about integrability, this is something related to the lattice mismatch, and performance is related to the bandgap energy. You see, between germanium and indium arsenide, germanium has a slightly better price and better integrability on silicon. That means if we can work on the integration problem of germanium on silicon and make the sensor so tiny, so reducing the cost of fabrication, we can actually make all these 3 metrics by using germanium grown on silicon. So now I will tell you how germanium can be used to detect infrared radiation. This is the band diagram of germanium with incoming infrared photon. This infrared photon can excite electron into the conduction band and creates a hole in the valence band. If the electric field is applied on the band energy, this band energy is getting bended and forming sort of like a subatomic slide, if you like. And this subatomic slide can make electrons and holes slide and flow. These flowing electrons and holes are essentially electrical signals that we detected. Of course, this picture assumes that the germanium crystal is so perfect without any imperfections. In reality, imperfections in the crystal create unwanted energy levels, and this energy level could disturb the flow of electrons and holes. For example, let's consider if we have a single imperfection level near the conduction band edge. This level could disturb the flow of electron because electron initially flow, but it can jump down and actually trap in this level. That means the electrical signals that we counted will get smaller. This is considering only a single imperfection. The problem is when we grow germanium on silicon, which is commonly occurred in vertical direction, atomic imperfections are generated that looks like bunches of half loops inside the germanium layer. And this, you see, this happens because lattice mismatch between germanium and silicon. These half loops looks like the following in electron microscope. And we have seen how these imperfections will degrade the performance of our detector. So this is a really challenging problem in the community. And in the laboratory, we ask ourselves a question. Can we make the very first half loop of imperfection and make it extended and make it reside in the bottom at the interface between these two materials, other than creating another half loop, another one, another one? Our hypothesis is that by growing the germanium crystal in horizontal direction can do just that. And here is how we tested our idea. To grow the crystal laterally, we prepare crystal growth templates we called microcrucible. This microcrucible composed of a capping layer and a gold catalyst. Okay, so you see, this works just like casting, but casting, so tiny casting in microscale dimension. This is the actual microcrucible on top view under electron microscope. You see, to get this tiny, tiny dimension, we need to use sophisticated microfabrication techniques. And this include PECVD, which stands for plasma enhanced chemical vapor deposition, to deposit the capping layer materials made of silicon dioxide and silicon nitride with the help of plasma. As we introduce this microcrucible with germanium precursor gas at 375 degrees C, we can actually make the germanium to crack preferentially on the gold catalyst, and this results in the nucleation of crystal inside the crucible structure. So as we expose more and more germanium, the germanium gets thicker and thicker, and because of this presence of the capping layer, this germanium crystal will force to grow in lateral direction. So with this, we can make the germanium to grow in lateral direction as we want it. And this makes the very first imperfection to extend it and residing in the bottom of the interface of these two materials. As a result, we can get a very high quality of germanium directly on silicon substrate. You see, as we grow from left to right, our imperfection is staying in the bottom at the interface of germanium and silicon. So this is really, really interesting result we got. And furthermore, we're also able to control the size of the germanium film by controlling the size of the gold catalyst. And if you have friends which are chip designer, this is a really big news, because in reality, in the chip design of optical circuits, we need those optical sensors and lasers to have precise dimensions. And we can control the size by controlling the gold catalyst size. In the slide, the experimental data shown in the blue dots, and the red curve is our model. You see, there is a really strong agreement between our experimental data and our theoretical model. So this demonstration have shown a possibility that our technique can be used to make optical fibers possible to be installed inside the data centers. And this way, we no longer need those cooling systems worth of thousands of terawatts of electricity. And furthermore, we can change all the copper wires in your smart devices, your laptop, your mobile phones. We can change to optical fiber. And this not only exciting because it's energy efficient, but it will make light speed optical computing much, much more closer to reality. Thank you very much for your attention.